Recrystallization, assessing effectiveness and a case study. In this webcast, we will discuss how to assess the effectiveness of a recrystallization. We will then apply those ideas to a recrystallization case study. There are two main criteria for judging the effectiveness of a recrystallization. The first is the compound pure? The purpose of a recrystallization is to purify your compound. To do this, you will use melting point, which is the subject of the second webcast for this week. The second criterion is how much of your compound did you recover. Retrieving pure compound is great, but if you started with 100 grams of compound and got only 1% of it back, it cost you a great deal. To help us gauge just how much of our compound we got back, we will use something called percent recovery. Percent recovery is a measure of how much of your compound was recovered from the original sample. Generally, higher values are better. However, there are exceptions. For example, if half of your starting material was impure, then a percent recovery of 50% would be great. Calculating percent recovery is quite simple. It is simply the amount of mass you recover, the mass of the crystals you collect, over the initial total mass, the mass of your original impure sample, multiplied by 100%. Let's say we had 10 grams of a sample of contaminated caffeine, and we recovered 9.1 grams. What was our percent recovery? Well, from the equation up above, we know that the recovered mass, which is the mass of crystals we got at the end, over the initial total mass, times 100%, gives us our percent recovery, which in this case is simply 91%. Now, that's a pretty good number, but there is a caveat here. Percent recovery tells us nothing about purity. If we got a 91% recovery, but our sample is still impure, then even though that number is high, our recrystallization failed. The take-home message from this slide is that higher percent recoveries are better so long as your recovered crystals are pure. This leads into an unfortunate fact about recrystallization. Here on the slide, we have the solubility of a compound called benzoic acid in some solvent at two temperatures, 25 degrees Celsius and 100 degrees Celsius. At 100 degrees Celsius, 6.8 grams of benzoic acid will dissolve in 100 milliliters of our solvent. At 25 degrees Celsius, 0.34 grams of benzoic acid will dissolve in 100 milliliters of our solvent. The question I pose to you is, if we took a pure sample of benzoic acid, would we ever get 100% recovery? Pause the video, take a minute, and think about it. Okay, let's talk this through. As you can see, at the cold temperature, benzoic acid has some solubility. It is not very much, but it is some. Therefore, some of the benzoic acid will remain in solution after the recrystallization. This means that no, it is not possible to ever get 100% recovery, because some of your compound will always be soluble in the solvent. When performing a recrystallization, the goal is to purify your compound. However, if you lose half of your compound in the process, that doesn't sound very efficient, does it? What can we do to maximize our percent recovery? Remember, solubility depends on the temperature of the solvent and on the solvent volume. Lowering the temperature lowers the solubility. Cooling to 0 degrees Celsius in an ice bath will give us a better percent recovery than cooling to room temperature. We should also use as little solvent as possible while still dissolving all of our sample. Remember, the more solvent you use, the more of your material that remains in solution. By using the bare minimum of solvent, you minimize the amount of your compound you leave behind. Let's apply these ideas that we have learned to a case study. Let's say I give you a sample that contains 10 grams of compound A, 1 gram of impurity 1, and 1 gram of impurity 2. The solubility of A, impurity 1, and impurity 2 are listed here in this table. The question is, how are we going to remove impurity 1 and impurity 2? Let's look at the solubility table. I see that impurity 1 is insoluble when the solvent is cold and insoluble when the solvent is hot. This tells me that impurity 1 is an insoluble impurity. It will not dissolve at any temperature. If we look at impurity 2, we see that it will dissolve to some extent at cold temperatures and should dissolve completely at high temperatures. The same with compound A. That tells me that impurity 2 is a soluble impurity. So, how are we going to separate impurities 1 and 2 from A? Well, we know impurity 1 is an insoluble impurity. Therefore, we can remove that through a hot filtration. If we take our sample, dissolve as much as we can in hot solvent, impurity 1 will remain a solid, and we can remove that through a hot filtration. If we take the solution that passes through the filter paper, which contains compound A and impurity 2, we know that impurity 2 is a soluble impurity. Therefore, we should be able to remove that through a recrystallization. Let's go ahead and say that we have removed impurity 1 through our hot filtration. We now have compound A and impurity 2 still in solution. We perform a recrystallization and we successfully purify compound A. How much of A did we lose in this process if we used 100 milliliters of solvent? Well, we know the solubility of compound A. We know that at the cold temperature, 25 degrees Celsius, 1.0 grams of A will dissolve in 100 milliliters of water. We are using 100 milliliters of water. Therefore, 1.0 grams of A is still dissolved in solution after the recrystallization. To say this again, we know the solubility of A via the solubility table. And we know the volume of solvent used from the question, telling us the amount of A left in solution. Okay, so that's not so bad. We're not leaving that much behind. But let's say I don't want to leave 1 gram behind. I want to minimize the amount of material that I cannot retrieve in this recrystallization. How can we do this? In other words, how can we maximize our recovery? Well, remember, there are 2 things we can do. We can try to cool our solution using an ice bath. Let's say we don't have access to ice or anything else that can chill our solution. What else can we do? We can also change the amount of solvent we use. Just how much solvent do we need to ensure that all of impurity 2 stays in solution at the cold temperature? To answer that question, we again look at the solubility table. We know that we have 1.0 grams of impurity 2 in our sample. From the solubility table, we know that 1.5 grams of impurity 2 dissolve in 100 milliliters of water. That means to dissolve 1 gram of impurity 2, we need 67 milliliters of H2O. To say this again, we know that we have 1 gram of impurity 2. I want to use just enough solvent to keep impurity 2 dissolved at the cold temperature. By minimizing the amount of solvent used, we lower the amount of compound A we leave behind. We know the amount of impurity 2 in our sample and the solubility of impurity 2 in water, our solvent. We calculated the volume of water needed to dissolve all of our impurity at the cold temperature. How much of compound A is left behind using this volume of water? Well, we're using 67 milliliters of water. And we know the solubility of A from the solubility table. Do some quick math. We leave behind 0.67 grams of compound A. This is significantly less than the 1 gram of compound A we lost using 100 milliliters of water. By using less solvent, we still remove all of impurity 2 while minimizing the amount of compound A we leave behind. That brings us to the end of this webcast. To recap, recrystallization effectiveness is determined by the purity of the isolated compound and how little compound was lost to the solvent through the use of percent recovery. You will assess the purity of a compound via a melting point analysis in this experiment. We will talk about melting points more in the melting points webcasts. Percent recovery is a measure of how much compound was recovered from the initial impure sample. You can increase your percent recovery using colder temperatures when shielding your solvent and/or using a lower volume of solvent.